My name is James Brown. Ow! I feel good. And I thank you for attending this workshop on practical use of the blower door.
Today, find out how airtight is a Triboard home. Why low-grade windows are the gift that keeps on taking. Some simple and affordable improvements you can make right away. When an HRV is not an HRV. And finally, we get into the weeds with a deep energy retrofit and have a look at what it will cost. The simplest way to describe a blower door test is a simulation of wind blowing on all four sides of the building at the same time. It's just a simulation, but it's a pretty reliable and accurate way of testing buildings relative to all other buildings. It's tethered to a gauge called a manometer that can measure the pressure difference between inside and outside, as well as the flow rate across the variable speed controlled fan. The standard test pressure around the world is 50 Pascal. That's like exerting 5 kilograms of pressure on every square meter of the shell of the house. Of course, the wind doesn't always blow on all surfaces of a house at once. In fact, it probably never does. It's actually worse. The side facing the wind is subject to infiltration, and the opposite side is subject to exfiltration. And even on a day with no wind, there's always stack effect that causes the building to constantly lose energy. An older home, say pre-1950, might have leakage of 10 air changes per hour or more under the blower door test. Meaning that, at 50 Pascal of test pressure, the house will leak 10 times its internal volume of air in 1 hour. If a boat leaked water at that rate, it would be sunk in 6 minutes flat. Recent research and testing shows that currently, the median leakage rate of new homes being built in New Zealand, as of this recording, is about 5 air changes per hour at 50 Pascal. And while that is an improvement over most older homes, it's still much leakier than the new home requirements in most of Europe and North America, and it's 8 times the leakage of a passive house. So how did our Triboard house do? Let's get the numbers. Well, at just under 3 air changes per hour, it's about 40% tighter than the current national average for new homes. That is better than I expected. The blower door is the kind of test, well, you really just can't fake it. Literally, leaks come out of the woodwork. And the window and door frames are not very high quality, so it's no big surprise that most of the air leakage is coming in there. But the Triboard system actually exceeded my expectations. In fact, the only detected leakage points in the Triboard linings at all were a handful of these power points in the exterior walls, where, ironically, the wires were routed through the exterior cavities. It's a mystery to me why Durapanel, the panel fabricators, actually specifically suggest doing this in their manual, in spite of the fact that the panels are designed to accommodate wiring. We'll need to seal these up from the outside with mastic or tape during the next phase of the project. The Durapanel manual also calls for a DPC, or damp-proof course, which is a thin strip of bituminous felt paper, or more recently, plastic, placed under the exterior wall frame. While this protects against moisture wicking up from the concrete floor, it is basically worthless as an air seal. All new homes should be using either a compressible gasket like this, or a concrete-compatible tape. For Triboard home retrofitting, a low expansion canned spray foam will do the trick. Also, it's hard to say without removing the cladding just how much leakage around windows and doors is attributable to the frames themselves or to the seal between the window frame and the air barrier. So why would the windows themselves be so leaky? Assuming the windows got sealed well to the weather barrier, many of the windows themselves are not very airtight. That's because most of the windows are actually sliding glass door panels, and there's 10 of them, plus the main entry, plus the door out to the garage. That works out to over 50 meters of weather stripping, not with gaskets, but with brush seals. What? A brush? But why? Refrigerator doors have gaskets. But that's to keep the cold air in. Huh?
So, like air conditioning, huh? Airplane doors, gaskets. Spaceships, gaskets. But these doors have brushes. Well, they can't be too tight. Why? Because then they won't open. Isn't there a solution for this? Well, they do make lift and slide doors.
Hey, that's a gasket.
Let me guess, they cost more? But won't they pay for themselves through energy savings?
Look, I get it. New Zealand is a gorgeous place, especially here in Queenstown. It's a no-brainer that you're going to want to have high visibility to the stunning views all around you. So yeah, sometimes you need 10 glass doors. But there's real discomfort consequences when someone chooses to downgrade on windows and these large door frames. It just irks me to see the drapes moving when the wind blows in through our brush seals. Alright, that's enough bloviating on what could have been done better during the build. I think I've covered that enough in my first 2 clips about this project. For this episode, I'm going to look at how I'm going to make it better. So now we have this key piece of baseline data from the blower door test.
Take it from Dan Brown. The blower door works.
Our friend Arthur Lee, who is a Queenstown-based architect and certified Passive House consultant, generated an energy model of the house using Passive House Planning Package software, or PHPP, to create some retrofit scenarios. Each scenario in this graph shows the reduction of heating demand expected for those improvements. Please like and subscribe if you support this kind of content and want to see more of it. The pre-retrofit heat demand of the house was over 160 kilowatt hours per meter squared annual. That's about 10 times the demand for a passive house of this size, which is sadly pretty typical. The as-built insulation scheme was just way too thin. The original 150mm attic insulation batting is a poor choice for attics built with trusses. There's just too many obstacles to fit the batting around, and frankly just too time-consuming to trim the bats into every geometric nook and cranny. A blown-in fiber like natural wool or blown fiberglass is much more effective at filling all the gaps created by the truss cords and other obstacles like lighting, wiring, electric boxes, and ductwork. And it's fast. Our attic was insulated in half a day by 2 guys. The results are phenomenal. Much cooler in the summer, and the metal roof is now much quieter in heavy downpours, and of course, there's less heat loss in the winter. DuraPanel should also add a requirement in the specs for a raised heel roof truss that is at least 60 centimeters above the ceiling panels. This would accommodate more insulation with enough space left over for attic ventilation flow. We've already completed the attic insulation upgrade and the foundation slab edge retrofit. These first steps have already yielded a noticeable change. Up to this point, we have now installed the upgrades with the maximum impact for the least dollars spent, and there was essentially no disruption in occupancy and almost zero waste. This was the no-brainer stuff. Older homes usually have many more opportunities for winnowing down the energy demand before getting into big-ticket items. But most of the usual suspects in older homes are just not here. The house is pretty simple. No chimneys, no chases, no furnace flues, no crawl spaces, no knee walls. The attic scuttle door is tightly sealed and insulated, and the walls are, well, solid. So to really move the needle much further, the next step is a bit of a cliff. While a window and door upgrade would be the most impactful of all measures, it would also be the most costly, the most disruptive, and the most wasteful in terms of materials. But living with inferior thermal comfort is not an option for us either. So, window replacement. Thermally broken, triple pane, airtight windows that are suitable for this location. It's the most impactful because it would address both the air leakage and the cold window surface temperatures, reducing heating demand by over 20 kilowatt hours per meter squared annual. But to do it properly, ensuring durability and weather tightness, the cladding must be removed to gain access to the edges of the weather barrier to ensure continuity of the membrane. And this would be precisely the moment to wrap the exterior of the building with an additional 70mm thick layer of wall insulation. These combined steps are the knockout punch, reducing the heating demand by 80 kilowatt hours. The existing 70mm wall cavity inserts alone would simply no longer be permitted in similar climate zones of Europe and most of the United States. X-Pole is a very good quality insulation, there's just not nearly enough of it here. A house in Fiji and a house in the snowy highlands of Queenstown have very different heating demands. but the current DuraPanel specs, as of this recording, call for the same wall and insulation scheme regardless of the home's location. That just defies reason, even if the building code currently allows it. Instead of simply meeting the minimum code requirement, DuraPanel should consider a bold move to a much higher wall and roof spec that can meet at least the new Homestar 8 Plus standard and even the stringent Passive House standard. This is the kind of differentiation that would make their innovative system future-proof and would keep it competitive with the energy performance benefits of structural insulated panel systems that are steadily gaining popularity in New Zealand. The final step is absolutely critical, and yet it's probably one of the most poorly understood. Should a house even be airtight in the first place? Well, decades of research and data show that the healthiest and most comfortable living environments feature high-quality ventilation systems paired with, you guessed it, extreme airtightness. Again, it's about control. If you've ever driven through a dusty patch of road construction, you instinctively roll up the windows, right? If your car was made after 2000, it most likely has a cabin air filter, and possibly even a recirculation mode button. And all of these functions and more are now controlled by the car's computer. And it's not just a luxury car thing anymore. Even mid-price range cars are coming to market with a network of sensors and controls to constantly monitor and adjust the microclimate inside your car. So why, with all the climate control amenities available to us in our cars now, why do we still build houses with very poor control over the same conditions? A house is typically 10x the value of your car, yet nowhere near as technically advanced. The internet would absolutely melt down tomorrow if Tesla started making cars that leaked tons of unfiltered air into the interior. So why are we okay with this from our houses? In most of the world, an HRV, in a building ventilation context, refers to a heat recovery ventilation system with some sort of heat exchanger, except for in New Zealand. Our house was fitted with a positive pressure ventilation system, or PPV, manufactured by a company called HRV. There is no heat exchanger in a PPV, just a little fan that blows fresh air into the house from the attic. Yeah, the attic. When it's feeling a little stuffy at home, don't you want to take a deep breath from the attic? PPVs are nothing new, but referring to them as HRVs would seem to be unique to New Zealand.
Filtered air comes in from up in the roof. Woof.
But any heat recovery has a pretty limited Goldilocks margin. Most of the time, the air is just too hot or too cold. And on some days, the humidity level outside might even be worse than the interior. The idea behind a PPV is that, theoretically, during winter, there should be occasions where the sun's rays heat the attic space to a temperature warmer than the living space below. And that warmth could be scavenged to supply warm, fresh air to the interior. The issues with this are manifold. Assuming that you can effectively filter out the insulation fibers, dust, pollen, and other particulate pollution present in a typical attic space, there are still only limited opportunities for using that air without simply increasing the workload on the existing heating and cooling systems. An attic in the summer can easily reach temperatures of 50 degrees C, and assuming that the roof is vented to the outside, as it should be, the winter attic air can quickly drop below the temperature of the living space underneath. Then there's the question of where does that pressurized air go? In New Zealand, positive pressure ventilators are marketed as a way to lower moisture levels in the house and improve air quality by reducing mold risk. But different houses leak different amounts of air through different places. His house might leak more out of this crawl space underneath, her house might leak through the old windows, while the guy's next door has leakage through recessed ceiling lighting back to his attic. In which case, it's just being recirculated by the PPV over and over again.
The wheels on the bus go round.
It's no wonder there's so many confused homeowners in these forums and chats, asking why they still have condensation issues and why they are getting different results than others. And a PPV is even less ideal for a higher performing house where the leakage is very low and cold surfaces are minimal. Once we have reduced the air leakage of the house below 3 ACH50, it's critical that air quality gets managed with a dedicated ventilation and filtration system with energy recovery. Unlike a PPV, a true HRV does scavenge waste energy, and it does it 24 hours a day, all year long via a heat exchanger. And the air is sourced not from the attic, but from the outside. The micro ducts are semi-rigid and of course airtight. They're flexible enough to route deep under the attic insulation to mitigate any thermal losses. The house is an elongated form, so we're planning for 2 smaller HRVs, one at each end of the house. That'll keep the duct lengths very short. A good quality HRV will recover up to 90% of the energy that would normally be lost by a PPV, or typical bath vent. That gives us another significant reduction in the heat demand while providing premium indoor air quality. The final item suggested in the energy model is to further improve the performance of the concrete floor. We insulated the outside perimeter edge of the slab, but the bottom of the perimeter, here, is not feasible to reach without undermining the integrity of the building. But it is feasible to lay down a so-called frost wing. This has the effect of slightly raising the temperature of the ground under the bottom of the wall and subsequently the temperature of the perimeter of the floor. It's a minor point in energy savings, but it could make a difference to the thermal comfort. 2 layers of 35mm X-Pole platinum rigid foam allows for offsetting of the wall seams for the greatest thermal continuity, though some manufacturers offer a shiplap keyed edge to accomplish this in one go. Either way, that's a total of around $6,000. Fasteners, tapes, and flashing detail membranes will be around $1,500. About 50 lineal meters of additional cedar cladding will be needed for repairs and slight changes to the overall house dimensions from the thicker insulation. Cedar prices are pretty volatile, so we're allowing $800. A true HRV system is about $10,000, including the ducts and registers. The complete package of UPVC triple-pane color-matched windows and doors includes the lift and slide door units, the swung entry door, the garage access door, the tall vertical windows, and the narrow horizontal windows, all with German tilt-turn function. The quote for this is around $80,000 plus GST, delivered to the site. That's about 25% more than standard double-pane aluminum frame joinery, but the thermal comfort is vastly different. At current construction costs in Queenstown, the better windows, thicker insulation, and better ventilation would be about a 5% increase in the overall cost to build from scratch. So, on a new home, these upgrades would pay for themselves in under 10 years. But the overall increase in air quality and quality of life is priceless. In the colder climate of the South Island in particular, homes are still being built by the thousands to a standard that's far behind most of the G7 countries, with little to no official verification of energy-related measures, especially air tightness. As it has within the European Union and the UK, there will likely be home energy rating requirements to sell real estate in New Zealand in the future. At that point, homes will have to be retrofitted one way or another to stay competitive with other higher-performing homes as the market matures, and higher performance gradually becomes the norm. Mortgage banks such as ANZ and ASB have already introduced lower mortgage rates for Homestar compliant buildings in collaboration with the central government. In conclusion, our Triboard home retrofit as modeled will just reach Homestar Level 7. The remaining hurdles to push beyond Level 7 would cost more to rectify than to simply rebuild the house. Passive House retrofit certification would be just out of reach, but I think we can be pretty happy with a vastly improved Homestar house that follows most of the Passive House principles. If you have a suggestion for a better detail, method, or means, please drop a comment below. Thanks for watching.